This black hole did something it was never supposed to do. It changed direction. Not slowly, not over millions of years, but abruptly enough for astronomers to notice in real time. And the moment they did, every standard explanation failed. Because black holes don't steer, they don't drift, they don't respond to gentle forces. A supermassive black hole weighs billions of times more than the sun. Its gravity dominates everything around it. To change its direction, something had to push back, hard. This wasn't a glitch, it wasn't a bad image. Multiple observatories saw the same thing. A powerful jet of energy, once stable and straight, suddenly tilted. And when scientists traced that jet back to its source, the implication was chilling. The black hole itself had reoriented. That single observation triggered emergency reviews across astrophysics teams worldwide. Because if a black hole can change direction, then something in our understanding of gravity is incomplete. The object at the center of this mystery sits billions of light years away, embedded in a distant galaxy that until recently looked unremarkable. For decades, its behavior matched expectations. Matter spiraled inward, energy blasted outward in narrow jets. Everything was aligned. Then the alignment broke. At first, researchers assumed an internal wobble. Accretion disks can be messy, magnetic fields can fluctuate, but this wasn't surface chaos. The angle change was too clean, too coherent. And worse, it kept evolving. Over days, the jet continued to drift like a compass needle being pulled by something unseen. Calculations quickly revealed a problem. The energy required to rotate a black hole of this size exceeds anything produced by stars, supernovae, or normal galactic processes. This wasn't a bump, it was a shove. That realization reframed the entire event. Astronomers weren't watching a black hole misbehave, they were watching it react to an external force powerful enough to torque spacetime itself. And once that possibility entered the discussion, the list of explanations became very short. Either another massive object passed extremely close, or something far stranger happened, something we don't yet have a name for. This video is not about speculation for its own sake. It's about following the evidence step by step, from distorted jets to warped star orbits, to understand what could possibly force one of the most massive objects in the universe to turn. Because whatever caused this didn't just move a black hole, it revealed a weakness in the rules we thought governed the cosmos.
To see why this matters, you need to understand what it takes to move a black hole. A supermassive black hole doesn't float freely. It sits at the deepest point of a galaxy's gravitational well. Stars orbit it. Gas spirals into it. Its orientation is stabilized by enormous angular momentum built up over millions of years. Changing that orientation is like trying to spin a mountain using a feather. Even galaxy collisions struggle to do it cleanly. Yet the data shows a measurable shift, so scientists looked outward. They examined the motion of nearby stars. What they found made the situation worse. Several stars close to the galactic core were no longer following their predicted paths. Their orbits had stretched and tilted, as if the gravitational center itself had shifted slightly. This ruled out a purely internal process. The entire system had been disturbed. Attention turned to the possibility of a close encounter. If another black hole passed nearby, its gravity could exert torque. But such an encounter would produce violent gravitational waves. Those waves were not detected. The signatures were wrong, too structured, too smooth. Instead, researchers identified something else, a faint, linear trail of energized gas crossing the galactic center, a wake. Whatever passed through was massive, compact, and moving fast, extremely fast, fast enough to spend little time interacting, yet strong enough to leave damage behind. This led to a disturbing hypothesis, a rogue black hole, not anchored to any galaxy, a black hole ejected long ago during a violent merger, traveling through intergalactic space like a gravitational bullet. Simulations had predicted such objects could exist, but they were considered rare and nearly impossible to detect, until now. A rogue black hole passing close to a supermassive one could exert a brief but immense gravitational pull, enough to twist jets, enough to disturb stellar orbits, enough to change direction. But even this explanation strained the data. The trajectory implied acceleration, not deceleration. Whatever moved through the system wasn't slowing down, it was gaining speed, and that shouldn't happen without continuous force. Which raised a deeper question. What if the black hole didn't collide with another object at all? What if it interacted with a moving distortion in space-time itself, a gravitational structure with no visible mass, something capable of transferring momentum without leaving behind matter? That idea was once considered purely theoretical, but now the observations were starting to line up uncomfortably well.
The strongest clue came not from light, but from time. Instruments designed to detect gravitational disturbances began picking up steady, repeating signals. Not the sharp chirps of black hole mergers, but slow oscillations, pulses. Each pulse aligned with changes observed near the black hole, and the timing was precise, almost mechanical. This was not random turbulence, it was periodic. Periodicity in gravity is rare. Space-time usually rings once and fades, but this signal persisted. That suggested an ongoing interaction, something moving through space while continuously disturbing it. When researchers modeled the waveform, they found harmonics, layered frequencies stacked on top of each other. This should not happen in standard gravity, but it does appear in exotic models involving space-time defects. These are theoretical structures predicted by some versions of fundamental physics, not objects in space, but distortions of space itself. Imagine a wrinkle moving across a stretched fabric. The fabric isn't broken, but everything touching the wrinkle is forced to move. If such a structure passed near a black hole, the effects would be dramatic. The black hole wouldn't absorb it, it couldn't. Instead, it would respond by reorienting, by changing direction. This would also explain the repeating pulses. The distortion would continue moving, sending ripples behind it. When astronomers mapped the direction of those ripples, they noticed something unsettling. They pointed toward a vast region of space previously thought to be nearly empty, a cosmic void. But new data revealed faint gravitational lensing there, light bending around something invisible, something massive enough to warp background galaxies. That meant the void wasn't empty at all. It was hiding something, a large-scale gravitational structure, possibly connected to the event that moved the black hole. If true, this changes the story. The black hole didn't randomly turn. It was influenced by a larger architecture of the universe we're only beginning to detect. And if such structures exist elsewhere, then black holes may not be the ultimate anchors we thought they were. They may be participants in a deeper gravitational network, responding to forces that don't emit light, don't collide, and don't behave like matter at all. This doesn't mean physics is broken, it means it's incomplete, and the universe has just given us a rare hint of what's missing. What makes this discovery unsettling isn't just what happened, but what it implies going forward. If a supermassive black hole can change direction due to an external gravitational structure, then no region of space is truly isolated. Even the heaviest objects respond to forces beyond their immediate surroundings. This forces astronomers to rethink long-held assumptions about stability on cosmic scales. Galaxies may not be as fixed as they appear. Their cores may be subtly influenced by passing distortions, invisible currents shaping their evolution over billions of years. Right now, scientists are monitoring the system closely. The jet continues to evolve. The surrounding stars remain displaced, and the gravitational pulses have not stopped. That suggests the interaction is ongoing. Whatever caused this is still out there, still moving, still affecting spacetime as it goes. The concern is not immediate danger. These processes unfold over astronomical distances and timescales, but the scientific implications are enormous. Dark matter, space-time geometry, and black hole dynamics are no longer separate topics. They may be different expressions of the same underlying structure. This event provides a rare natural experiment, one we didn't plan but desperately needed. A chance to observe gravity behaving outside familiar boundaries. For decades, black holes were treated as endpoints, ultimate sinks, but this observation suggests they are also sensors, reacting to deep cosmic forces passing through the universe. If confirmed, this would mark a turning point in astrophysics, not because a black hole moved, but because we finally noticed what moved it. The universe didn't change its rules overnight. It revealed a rule we hadn't seen before. And now, astronomers are watching closely, because the next shift may not be subtle, and the forces responsible may be far more common than we ever imagined.